Hello everybody, my name is Isabella and I'm a master student from Germany, part of the Conodont fan club at FIU in Erlangen. That's me, so you have a face to that background voice. And obviously my research focuses on conodonts, the earliest vertebrates bearing the mineralized skeleton, which makes them a great subject of the ongoing debate about their affinity, function and their evolution. I want to share with you my ongoing research project about how to explore the feeding behavior, ecology and the internal morphology of early coniform conodonts, which is directly linked to the origin of predation in the earliest vertebrates in the fossil record. The oropharyngeal cavity of conodonts contained an array of phosphatic dental tools known as elements, which are the most commonly preserved part of the animal. They functioned as teeth, used for grasping and mechanical digestion of prey. Conodont elements range from more primitive, simple cone-shaped coniform forms, as we see here, to comp-like, more complex forms. This morphological diversity reflects their rapid evolution, but however, most studies had been carried out on complex conodonts, while there is little evidence about how feeding strategies evolved within these very early coniform forms. All euconodonts, also called the real conodonts, are derived from the more primitive paraconodonts, and all of them are composed of fluorapatite and are internally constructed of two types of tissues, the enamel-like crown tissue and the dentine-like basal body. Even though they had similar protective function to the classic enamel and dentine, they evolved independently and convergently to vertebrate teeth. Furthermore, conodont elements grew by periodic appositional accretion of new lamellar crown increments, which preserves wear patterns and damage on tissue surfaces. Several studies of growth dynamics and wear fractures on complex conodonts have been carried out, but growth dynamics of the simple coniform conodonts are nearly unknown. I am working with Panderodus and the more primitive Proconodontus, two coniform conodont genera which are quite distantly related in space and time, but have had similar morphology and also most likely similar function. One graciliform element of Panderodus has been selected and one symmetrical aquiliform element of Proconodontus muelleri. Both are referred to have had a grasping function while the animal was feeding. Panderodus has been selected because, besides being highly abundant microfossil, it is the only known coniform conodont represented by almost complete fused clusters and natural assemblages. Sansom et al. Developed in 1994 the best understood multi-element apparatus reconstruction for coniform conodonts, based on Panderodus, which simplified multi-element taxonomy and provided a very precise element identification for coniform conodonts in general. While the apparatus of Panderodus had 6 different element morphotypes, apparatuses of non-panderodontoid taxa had most likely lower morphological differentiation. Duncan Murdock added in 2013 functional interpretations for each element, dividing them into those with a grasping and those with a cutting function, based on element morphology and inferred mechanics. The graciliform elements are repeated several times within the apparatus, while the aquiliform element lies on the symmetrical axis. Apparatus reconstructions of Proconodontus are here more theoretically. The hypothesis I test here is that predation already existed among the earliest conodonts. I focus on comparing both coniform conodont genera because they represent a great source to study increased specialization within the conodont apparatus during evolution. Conodonts are so cool to study because they play an important role in the reconstruction of evolutionary relationships between form and function in vertebrate dentition. We test if the appearance of the apatite crown tissue was an adaptation to a predatory life habit. Those results will help to clarify how predation amongst the earliest vertebrates evolved. BSE and EDX analytical methods are used to explore the internal microstructure of biominerals, shedding light on functional morphology and growth pattern. I produced high-resolution BSE images to count and measure the thickness of growth layers. Those are used to verify if there are any internal wear fractures visible, to test how the elements were arranged within the apparatus and if they might were in contact with each other. Changes in the chemical composition, especially in strontium, were obtained by doing EDX analysis in order to test if strontium content changes throughout the element between different ontogenetic stages. In addition, I used synchrotron scans to explore the inner structure of Proconodontus without actually destroying the specimens. If you are interested in the very different and delicate preparation steps for the analysis, stay tuned to Bryan and SHIRLEY's presentation about the Conodonts and the Conodonts of phosphatic microfossil preparation and microanalysis. And please note here, all the results presented refer to the two specimens I introduced at the beginning. With the help of our high-resolution BSE images, I counted growth increments within the crown tissue in both specimens, and if we assume a daily growth rhythm as suggested for complex conodonts, Panderodus lived for around 1 month. Proconodontus seemed to have lived twice as long as Panderodus, around 2 months. We don't see different growth stages, neither in Panderodus nor in Proconodontus, but we see a slight change in the speed of growth, which can be detected in both specimens. We have fast growth during the juvenile stage, and then the growth dynamic changed towards the adult life by generally slowing down. Some minor elements, including strontium, are incorporated in appetite-forming tissues during the life of the animal, reflecting either their migration or changes in their diet. Because those conodonts might have had such a short lifespan, migration is less likely to influence the strontium content. Strontium was measured in both elements along several line transects, showing content differences between the basal body and the crown tissue. During such an EDX measurement, we do not measure absolute numbers, but we do measure the relative content as count per second. To test whether we see statistically significant changes in strontium content, I fitted a linear model to the measured strontium content of each line transect using the R software. The p-values got calculated using the LM function, which refers to the null hypothesis that the slope coefficient is different than 1, so for example that the trend does show a change. Special attention should be paid to changes in the crown tissue, as I marked in this BSE image. For Panderodus, we see a statistically significant increase towards the outer part of the element. The pattern we see here for Proconodontus is statistically not significant. In general, strontium in skeletal tissue is increasingly depleted relative to calcium, with each transition to a higher trophic level. In general, strontium content changes by either feeding on strontium-richer or strontium-poorer food. The relative content we see here does not allow telling the position in the trophical change without detecting any wear surfaces, but analyzing the strontium-calcium ratio could help, and in theory, a decrease would at least suggest a higher trophic level. So let's have a look. For Panderodus, we see again a significantly increase within the strontium-calcium ratio on both line scans, while the ratio in Proconodontus again does not significantly change. A whole other result, as I got obtained by SHIRLEY et al. In 2018. The complex Conodont Otsacodina, shown here, shows a significant decrease in the strontium content as well as distinct wear pattern. Additionally, 3 different ontogenetic stages were visible, while the animal started mechanical digestion of food from stage 2 on, so later in its life. But let's come back to my coniform conodonts. Strontium content or strontium-calcium ratio alone does not strictly refer to whether some animal fed predatory. To make a clearer statement, wear surfaces should be taken into account. In both of my specimens, I did not find any clear evidence of wear or subsequent repair at all. But still, I've made some conclusions out of the analysis already done on both of the specimens. Both have had similar growth dynamics, but Proconodontus seemed to live longer. We don't detect any wear fractures, which refers to an apparatus in which the elements might not have been in touch with each other. We can't make any clear statement about their feeding ecology yet, but however, Panderodus seemed to change its diet, while the less derived Proconodontus did not. So what do we have? No wear fractures are visible, neither in Panderodus or Proconodontus. and the strontium-calcium ratio does not decrease as we would expect for an animal moving towards higher trophic level. Overall, they did not undergo the same complex shift as more derived conodonts did. Maybe the situation is even more complex and complicated as we thought. Even though there are some quite unreliable hypotheses about their feeding ecology out in our scientific world, there could be also some germs of truth. So obviously, my research is not over here. We are gonna perform that analysis on several more specimens to get higher results in order to establish their ecological diversity and their feeding behavior. The open question, which functional adaptations were driving differences in the apparatus between both genera, should be answered by reconstructing the feeding apparatus of Proconodontus and to compare it to the existing one of Panderodus, as well as examine their element function and mechanics. A cluster plus synchrodon data can be useful to actually answer some questions about the earliest vertebrates in the fossil record. So that's it from my side. Thank you so much for listening. If you have any questions, feel free to contact me.